Yes, you're in the right room, just the wrong time. Do you have any questions about the project? I saw at least one person made it to the office hours, but you have no direct questions. Yes?
I have one about the knee.
Yes.
How does the joint is actually behaving? So it's like, is it, we can talk later.
It's two things rolling on each other, right? We had rolling on flat ground without sliding, and now we basically have rolling on a rotating surface, right? Which adds another degree of complexity, and but in principle isn't much different. But you basically, the weird thing is that you get, with rolling without sliding, you get a rotation that comes from the rotation, and you get a lateral movement which comes from the rolling. Now, if you roll on a curved surface, right, there's sort of this additional element of that rolling along the surface basically generates some change in orientation. But I would build this up step by step, start thinking about how is rolling on a flat surface, then think about how do things change if I roll on a circular surface, and then maybe go back, right? Whatever equations you derive. Of course, if you set one of the two radii to infinity, you should get the equations for rolling on a flat surface, right? So that's always a good way of checking your assumptions, right? And if you make one radius go towards 0, what does that mean, right? You end up with a pin joint. So these are always good checks. Yes, you also had a comment or question?
Still about the knee joint. And the coordinate, the generalized coordinates that we will need to use,
it's your choice, yes.
Okay, it's not that like that.
Whatever you want it to be, right? And that's, I mean, this is one of the reasons why we picked this joint, because you have to think about what's the meaning of a generalized coordinate in this context. There's obviously different choices. Some may be better, some may be worse, right? And for rolling on flat ground, we said it's the angle, but we could have also chosen the delta x, right? And that's a little bit the difficulty here. Yes. And whatever you choose, right, that's why we have the report documented in the report. And this is by design, right? The whole idea is not that everyone hands in exactly the same thing, right? The questions are on purpose very broad, very unspecific, so that we can accept a broad variety of solutions, and everyone will be able to show their own work. Whatever assumptions you make, why do you choose a particular generalized coordinate? Stated in the report. Second question?
Organizational is the two slots that you mentioned have flashes in both of them. So is there any possibilities to add any other slots, or in the future maybe?
It was hard enough to find these two, right? Because we have to coordinate room being free, TA being free. The other time that we have with Thursdays from 11:30 to Thursdays from 2 to 3:30, which of course isn't a bit pointless, right, to have this during our class time, but that's simply when the TA has time. You sent me an email already, did you? Yeah, you have to ask Iskander if he has some time, right? And of course, smaller questions we can always discuss before or after class. Okay. General piece of advice, and this is now life advice and not project advice. Whenever you have an engineering project that is somehow open-ended, the first order of business is to get a running solution. So try to simplify the problem to a point where you can have a working solution. That should always be step one, and then slowly increase the complexity rather than starting with the full complexity and doing basically a one shot at a solution. If you have a working solution and you work with little deltas, you change something here, you introduce something here, you can always go back to a working solution. And if it doesn't work, then you know why it doesn't work, because you just made that one change. If you do 5 things at once and it doesn't work, you have no idea which of these 5 things it was. That's life advice, right? You always should approach any problem that way. With respect to the project, it means think about how you can simplify things, right? There are these 2 new joints. So scrap that, right? Do a rotational joint first at the hip and the knee and see if you can get the general the general setup, the model running, and understand everything that's going on. And once you have that, then think about adding a hip joint. But maybe don't add a hip joint to a complex geometry where you have sort of your femur head offset and weird geometries and initial conditions, but maybe just try that joint in the simplest configuration that you can think of and make sure that it behaves as expected, right? So a ball and socket joint, of course, in a planar, if everything is planar, inertia, mass distribution, everything is planar, initial conditions, it should behave like a rolling contact, like a revolutional joint around 2 axes. And that way, right, you can check everything, start with simple things, see, okay, do I get this? Do I get that? What happens if I get a motion about the longitudinal axis? And very carefully build yourself up, right? And this is by design, right? That's why we say first simplify the project to a degree where you get it to work, and then start adding more and more things. Yeah, don't try to do everything at once. That's typically, a recipe for disaster. That was my life advice. I don't know if you needed it, but felt felt good. Any other questions about the project? On Thursday we have a exercise, and this is how ill-prepared I am, because normally I just have to click and show you the homepage, show you the homework, and not today, sorry, as I was hunting my pen. Tried to take pictures down there, but it's a black pen with about this diameter, which is stuck between black cables with about this diameter. So a big one. Here we go. Last exercise, collision and contact. What we will do in this exercise is basically take your robot, including the controller from the previous exercise, which is already able to move along a nicely predefined trajectory, and then encounter the scenario where a person, technical term is an idiot, left a wire in the workspace of the robot, and the robot gets entangled in this wire, right? And the wire is bolted somewhere at some point to the ground, and the other end is attached to the robot's end effector, and the robot is trying to do its move, right? Move in a straight line, and at some point, right, initially the line is slack, and then at some point it gets tensioned. So you get to compute a collision, and then you basically get a loop, constraint dynamics, because you go ground, link, right? The 3 links of your robot to the end effector, wire, ground. So you have a loop, and you get an interesting constraint. What's the constraint? If your end effector is basically the length of the wire is constraining the end effector, where can the end effector move? And in 3D, on a ball, right? And then you can actually say, because it's a unilateral constraint, it can move in a sphere. It can also move in the inside, but it cannot get out, right? So I'm not a good mime, but you can kind of imagine, right? You have to stay within that circle around the anchor point of the wire, radius, length of the wire. And that's the goal for Thursday's exercise. And you've seen, right, we do collision computation in the project, so this seems to be quite relevant. To prepare yourself for that, there's 2 homework problems. Problem 42, is there 2? I should double check this. Yes, 2 homework problems. 42 is a reading problem, talking about event detection in MATLAB. I mentioned this in our Thursday lecture because someone asked, how is this done? This is how it's done. If you are unfamiliar with this, read through the documentation. There may even be a small tutorial that you can do just to familiarize yourself. How can you monitor, detect zero crossings as event functions in numerical integration? Who of you has seen this? I guess half of you. Yeah. It's not rocket science, but of course, if you go through this, this will prepare you a lot better to understand what we're doing on Thursday. And then, this is rare, we actually do a pen and paper exercise. The thing here is that I want you to get a better grasp of when I say there's a constraint Jacobian J, right? So we have a constraint violation and a constraint Jacobi and a bias acceleration in this constraint space. I want you to get a little bit more familiar with these concepts, because then we, of course, have to figure out what's the constraint space for this wire situation. What's the associated constraint Jacobian? How do we set this up? What are the bias accelerations? Where do they come from? And so here we have a very simple example of a frictionless contact between a bar and a point. So you have to define what is the contact distance, compute the contact or the constraint violation, the constraint Jacobi, and so on. And you do this all by hand. And I think there may be a little MATLAB simulation that you should run to just verify your solutions. But the main work is in figuring out these Jacobians and accelerations and so on. Questions? No? Then let's go back to our example of this passive dynamic walker colliding with the ground. Right, so we had this system that I actually brought to you, and this is our abstract simplified model. And what I wanted to show you here, without going into all the details and actually talking about how to solve some of the problems, we will have to skip that, but I want you to be at least aware of these problems, is this idea of multi-contact, which is kind of nicely exemplified here. When I say this front foot goes into contact, I now have 2 unilateral contacts, one in the front, one in the back. I have a collision, and then I can basically think about this going 2 ways. Number 1, I have 2 collisions, one in the front, one in the back, which would mean that both feet would come to a complete stop. But there's a catch, right? Or there's a requirement. When I assume that, when I assume I have a collision in the back, and it really happens and brings that velocity to 0, the collision impulse, the vertical collision impulse, must be positive. Because it's a unilateral constraint, ground can never pull you down, it can only pull you up. I can also assume that the foot leaves the ground, then there's no collision, right? Then I would only compute the collision at the front. I will not have a collision impulse in the back. But again, I have to make an assumption, or I made an assumption, and that assumption is only valid if afterwards the contact point leaves the ground. So we get multiple possible outcomes, right? And there's you can think about this as a combinatorial problem, because here I have 2 contact points, but if I have a complex systems, I may have n contact points, right? And then I have 2 to the n different contact scenarios. In this special case here where we said friction is infinite, so if I'm in contact, I come to a complete stop. Whereas in reality, you could also have coming to a stop, sliding one way, sliding the other way, leaving the ground. So you have 4 cases per contact point, so 4 to the n different possible outcomes that you would have to consider. And you can see how something like that quickly scales up in complexity. The way we did it is we said we have 2 contact points. We know that the one in front is always going to be in contact, so we just have 2 scenarios. Scenario 1, case 1, the trailing leg leaves the ground. And that basically led to an additional assumption that we said this trailing leg impact has to be equal to 0, and left us with the leading leg impulse and the trailing leg velocity as unknowns, and we were able to solve these equations the way we set them up. And this here, that's the result, right? We have on the left-hand side, we have post-impact velocities. On the right-hand side, we have impulses. Bluish colors, leading leg, reddish colors, trailing leg, and then divided here by x and y direction. You see the assumption immediately here on the right-hand side. We said the trailing leg will not participate in the collision. Correspondingly, the impulse at the trailing leg is 0. That's nice to see here. The leading leg participates in the collision, and consequently, the post-impact velocity is 0. So both blue lines are solid at 0. I then can check here the leading leg vertical impulse, and I see that it's always positive. That's good, right? It's a unilateral constraint, but the leading leg comes to a stop. No matter how I choose this inner leg angle, the leading leg experiences a positive vertical impulse. This all checks out. So the thing that we have to look at is the trailing leg vertical velocity, this y dot. Can you see this well? I can zoom in a bit if you want to. So the red line here, that has to be positive, right? If it's negative, then we basically make the assumption ground is not there, right? There's no collision or there's no interaction with the ground. And then the solution tells you, okay, but then after the collision, you move down, you move into the ground, which is, of course, not possible. And we see that in the simplified system, for the parameters that we choose here, we actually only had to choose one parameter, which was this inner leg, this velocity factor between the rotation of the front and the back leg. But here we see there's, for small angles, there are valid solutions. And this happens to be 15 degrees. So for angles that are smaller than 50 degrees, my front leg hits the ground, front foot hits the ground, hind leg comes off. And this passive walker, this is what we saw in the demo, can continue to walk. Right? And this is when we hit the ground with a fairly small inner leg angle, we basically, in the collision, our hind leg comes off. Human walking is more complex because you have knees and ankles and ankle push-off and wobbling masses and. But in principle, this is how it works. In this range, the solution is invalid. Yeah, it makes sense. The assumption is leg leaves the ground. We do the computation. The result is the foot point moves downwards. That cannot be true with a unilateral contact. And then there's this range here in the back, right, which is an inner leg angle of close to 90 degrees, but we define angle on each side. So at this point, the robot is almost doing the splits. So it's don't do this ever, especially not next to openings. At this point, right, it's maybe not very relevant, but for angles larger than 75 degrees, this works out as well. Case 1, right? Then let's study case 2. Case 2 was both legs come to a stop, or both feet come to a stop. So I have a collision at the front, collision at the back. Again, we baked that assumption that the post-impact velocities are all 0 into our equations, which removed one of these 3 unknowns, left 2 unknowns that we could solve for. Here's the result for our choice of parameters. Of course, all post-impact velocities are 0, right? That's baked into our assumptions. That's what we see here in the plot on the left. So what we really have to look for are the post-impact forces, and the interesting bit are the vertical forces. In blue for the trailing leg, all positive. That's fine. In red for the trailing leg, where we have here a range where we say we make the assumption that there's a collision in the back, and then we compute the impulse, and the impulse is pulling the leg down, which is not possible because it's a unilateral contact. And then from here on, everything looks fine, right? Then the vertical impulse is positive. If you plug in the values, right, this happens here around 30 degrees. Does anyone see a problem? Yeah, what the heck is going on between 15 and 30 degrees? Right? We assume leg leaves the ground. Equations tell us it's moving down. Okay, it has to stay in contact. We assume leg stays in contact. Equations tells us, yeah, but you can only have that if there's an impulse pulling you down. It appears that there's no solution. That's problem number one. Good catch. Problem number two, even worse. For angles larger than 75 degrees, both solutions are valid. I assume leg leaves the ground. System says, yep, no problem, leaves the ground. I say foot stays on the ground. Solve the equations. Yep, you need a positive impulse. Right? If I apply positive impulse, I stay on the ground. If I don't apply an impulse, I leave the ground. What is going on? And let's maybe start with the first issue. Do you have an idea what happens between 15 and 30 degrees? And the trick here is to start reasoning about friction. Here I always assume friction is infinite. But if you think about this, right, if I have some finite friction, 1 is a fairly reasonable coefficient of friction, right? That's a rubber on rubber, I think, has 1, or tire on rubber has a coefficient of friction of 1, right? It's not a weird number. If I assume a coefficient of friction of 1, I can look at this and start thinking about when will this thing start to slide, right? It will slide when the horizontal force, or impulse, right, but it's the same thing, right, is equal to the vertical, right? Normal force equals horizontal force. That's sort of the critical point for a coefficient of friction of 1. And this will happen already here, right? So in this range, we still have valid solutions for very large coefficient of friction, but for reasonable coefficient of friction, at some point we will start to have sliding. And indeed, we have to go ahead and assume that we can have sliding with infinite friction. And that sounds first totally counterintuitive to say I have sliding with infinite friction. But friction, or coefficient of friction, is not saying you get infinite forces. It just says something about the ratio, or more precisely about the tangent of an angle. And I can very easily give you an example that doesn't even involve collisions, where I have motion despite the fact there's infinite friction. This is u, this point here, point y, u, and you're dragging a stick. The stick has some mass m, which generates some gravitational force g. And it's sliding on a ground that is flat, not flat in my picture, but flat in your imagination, and it has a coefficient of friction that's infinite. Right? And you initially say, okay, if there's a coefficient of friction that's infinite, I'm never going to be able to pull this thing. Right? And pulling the thing means you have to pull, and somehow you, of course, have to hold against the weight. But coefficient of friction of infinity doesn't mean that the frictional force is infinite. It just means that the friction force is a force that is purely tangential, right? If I draw an arrow like this, it has a normal force of 0 and some finite tangential force, and the ratio of these two, of course, is infinite, right? That's what mu equals infinite means. This would be your friction cone for some finite mu, and then if you increase your mu, it gets larger and larger and larger and larger, and for mu equals infinity, you get both directions plus minus 90 degrees. Now, with this, solving this problem actually becomes quite simple, because my horizontal force, my Fy, is going to be equal to the gravitational force G. Then I set up a balance of momentum about this point, which says that distance times G equals that distance times this force here, which gives me some finite friction force. And then, of course, this F, so this would be our F friction. And this would be the force with which I have to pull, which has to be equal to the friction force. And we're done, right? So infinite friction or an infinite coefficient of friction does not necessarily mean friction forces go to infinite. It's just about the direction. So there we made a horrible mistake on the very first page. Where's the very first page? Here, right? This is not true. Mu equals infinity doesn't mean you don't get motion. And I'm not doing this for the sake of time, but it basically means you would have to go ahead and introduce a third case where you say, I have sliding with infinite friction, which basically means I have no velocity in this direction and no force in this direction, but I have a force in this direction and the velocity in this direction. So this block structure, we have this 2x2 block structure, would have to be expanded to a 4x4 block structure, and you say, okay, I know something about vertical velocity and I know about something about vertical impulses, but horizontal velocity and horizontal impulses are unknown. And then again, I can go ahead and solve. And I could do the same for a case where I say I have some finite friction, where I say horizontal and vertical force are both unknown, but I know that their ratio is mu, right? And then you would basically get the case of sliding with finite friction. So these holes here, right, they can be patched, and they don't show up if you include regular friction, and if you have infinite friction, you still get sliding. Yeah, sounds weird first, but if you think about friction as simply being an angle constraint, right? It's not, my friction cone doesn't say how large the force is, it just says in what range it can be. And here the angle becomes, 90 degrees, and I still can solve this, still get some motion. You look puzzled. You don't believe me?
What is the formula for friction in that case? Like how large is the force in there?
Well, normally you say tangential force is mu times normal force, right? But for mu being infinity, that's kind of weird. So I could just write this as 1 over mu ft equals fn. And then this could be anything because I divided by infinity, so this is going to be 0. Right, so I'm just saying there's no normal force, but you still get a tangential force. That's weird, but this is what infinite friction means. Okay, I'll give you another example. Actually, it's the same example, but now here's my ground. I have a ground that consists of a ground, and on that ground I have these vertical spikes. Yeah, and instead of a stick, I pull a ladder, and the last spoke of the ladder is sitting in here. That has a coefficient of friction of infinity. Right? This is basically my definition of coefficient of friction of infinity are these spikes. But if I pull here, right, what will happen? Now I look at this as a dynamical system, right? If I pull here, what will happen is that this guy will move up, right? And at some point, because I have this angle, right? The trick here is to have an angle. And because of that angle, at some point, this thing will jump over these little spikes and then will continue to move, right? And so this is sort of the macroscopic view or microscopic view of this idea of sliding with infinite friction. I basically somehow have to generate an upwards force that compensates the mass. This is, I'm pulling the thing up. And at that point, my friction force is purely horizontal. You can try this, right? I believe you can try this, and it depends on the angle. If you're too low, you pull at an angle that is too shallow. This is not going to work, but if you pull high enough, that will work. That was actually the easy case, right? We were able to fix this. That range, right, at the high end, and you actually, when you include the case of infinite friction, you will see that it works as well. So you make the assumption, I come to rest, yep, checks out. I make the assumption, I leave the ground, yep, checks out. And you make the assumption, I glide against infinite friction, that will check out as well. And this is something that feels very uncomfortable, because when we talk about differential equations, we're so much used to uniqueness and existence, right, that we think of this as something that is always true. But uniqueness and existence are subject to conditions on your differential equations. One of them is that things are continuous. And of course, when we talk about collision, we basically leave the space of things being continuous, right? We're talking about jumps. We're talking about discontinuities that happen. Am I in contact? Am I not in contact? That's not a continuous process, but a discrete decision. I can also try to explain to you what the mechanism is. And it has to do with this contact space mass matrix lambda. And to reason about this, think of a rod. Has its center of mass somewhere in the middle, has a mass, and this thing also has some inertia, let's call it J, which is comparatively small against the mass. So, you know, this is made from styrofoam, and then there's a heavy lead core in there. Yeah? And it's sitting on a plane. Gravity doesn't play a role. And now I'm going to hit it with an impulse. So I will apply an impulse here, some capital lambda, which is code for I hit it with a hammer. Right? I'm not applying a finite force over finite time. I hit it with the hammer, so I force a collision. In infinite time, I apply an impulse. And the question is, in which direction will that corner move after, oh, sorry, I did this wrong. Ooh. Bad instructor. This is better. The question is, in which direction will that corner move after you hit it with a hammer? Down. Why? Right? You can think of this impulse as two things. There's a component along the rod and a component orthogonal to the rod. The component along the rod is simple because it's going to create some acceleration in this direction of the center of mass, which is going to be small because the mass is large. The impulse in this direction will also create an acceleration in this direction, which, given the angle, is actually a little bit smaller. It's also going to be small because mass is large. But hitting something that way is also going to generate an angular velocity or jump in angular velocity, which is going to be large because J is very small. So what you said is absolutely correct. This thing is going to move, maybe not perfectly in a circle, because I still have some motion this way, but let's say it's moving this way. So this is going to your C dot plus. OK? Mathematically, this comes from the fact that the contact space mass matrix, right? In this case, we have m lambda times c dot plus, right? Minus c dot minus, but that's 0, equals capital lambda. These are our equations. And this guy here is not a diagonal matrix. It has off-diagonal elements which create these couplings, right? You know, if I have a matrix times vector, the resulting vector is not going to be collinear unless the matrix is the identity, right? Or you hit it in, along an eigenvector, things like that. But in general, the direction in which I hit it and the direction in which it will move don't have to be the same, because this is a matrix that has non-zero diagonal elements. You all on board with this? Now, here comes the point where I can add ground. And I add a second impulse, a small one, very small one, that, what, lambda 2. This would be lambda 1, not lambda I, lambda 1. That happens at the same time. And now I ask you what happens. Right? And I assume that this impulse is generated through the contact. And now I can say, OK, if I only apply this impulse and there is no contact, this rod is simply going to move straight up. That's a valid solution. But then I say, OK, but actually, I want to assume that there is contact. Right? This is going to pull me up. But if there's a contact, there is sort of this additional effect that's going to pull the contact point inwards. So an upwards impulse is actually pushing you into the ground. Right? And this is exactly the effect that we get in our system, which basically leads to the fact that uniqueness of solutions doesn't exist anymore. And that's really, still for me, that's hard to stomach, right? But it's a consequence of the modeling assumption where we say everything is rigid. If you would look at this as a soft system where everything is deformable, then you would initially, of course, get rid of these discontinuities, and you would see that there are unique solutions. But that are, I don't want to say unstable, but that depend heavily on the initial conditions. Right? How do I choose my initial condition? If I'm penetrating a bit more, then I will stay in contact. If I penetrate a little bit less, I will leave the ground. And so I get a strong dependency on these initial conditions that I can only continuously set in a soft system, where I can say, OK, I have some soft penetration, right? And it's large, and then I stay in contact. If it's not large, I will not stay in contact. And then I make this process where basically my stiffness gets larger and larger and larger. And what that means is that these cases, stay in contact, leave, are getting closer and closer together. Right? I get a larger sensitivity, in a sense, on the initial conditions. And for stiffness going towards infinity, the distance in this initial configuration space, the distance between the solution goes down to 0. And one single prior state trajectory can branch off into 3 different trajectories. That's a consequence of our modeling assumption that was obviously wrong. Questions? It's OK if you don't understand this 100%. I just want to give you sort of an intuitive idea of what's going on here. I want to highlight that there are problems. If you're curious, what I should say at this point is that every roboticist that I know, including myself, makes these assumptions. And normally, they don't show up. But at some point, right, we tried to, actually preparing this for a class, we looked into this simplified version. Oh, let's make this simpler, and all of a sudden we were sitting there and what's going on, and realized that you cannot make these assumptions. So ultimately, I actually wrote a paper about this that deals exactly with this problem, because it shows up in models of soft robots, and all our colleagues ignore it, right? Sometimes rightfully so. We always make assumptions, but a lot of times they just didn't think about it. And here is some graphs out of this paper, which basically explain to you what I just tried to highlight here. So if you're curious, there's some reading material. Any other questions about collisions? Then I want to do a quick intermezzo, and this is me forgetting something before I started class, but this is now a good point before we move into the next topic. I want to quickly check who of you intends to take this class as part of our specialization area, robotics non-industrial. Okay, can I do this with names? We have Sarah, right? Was it? Yeah. Your name? What's your last name? Ah, yeah. There you go. But you go by a different first name, right? Nice. Okay. Who else? Sorry. What's your name? Sam. And last name? Oh. Yep.
I'm not sure yet. It's either specialization or system modeling and analysis.
Okay. And you're Ayman, right?
No, Salah, my last name.
Oh, sorry. Yep. Okay. Julius, right? Hoffmann. Yeah, that I remember. Markus Escher. Tobias. I have no idea what your last name is. Berger. We got it. Jan Keller.
Yes, I'm not sure.
Okay, I put a question mark. Yep. Say that again. Oh, yep. Got it. Okay. So where did this happen? Oh, there we go. And your last name? Oh, yeah. Got it. Om. And your last name is? Sorry, I'm not good at this. Can you say that again?
O-M, and my last name is D-E-O-R-E, Theory.
Are you registered for the exam?
Yes.
You sure?
Yes, I can see it in the portal as well.
Oh, yes, sorry. Noah. Hildebrand, yes. Did I have all? Did I catch all? Okay, now the real test is, do I remember all the new names? We'll get there. Thank you. This is just for stats. New topic. Actually, a bit of an add-on to this idea of contact space, contact forces, and projection methods. And this is our little robot. And we simulated a version of this in one of the exercises. I don't know if you remember, but when we did loops for the first time, that was our example, where we said we want to simulate this robot with a point foot, front and right. And then the simulation itself was pretty boring, because we said all the generalized motor torques tau equals 0. and then watched how this robot more or less gracefully collapsed, right? And we played around. What happens if I change the contact Jacobian and then it collapses on one foot, or it collapses on both feet, or if I disassemble or if I take out the constraints altogether, then everything falls through the ground. In general, of course, that's not what we want. We want a robot that walks, or at least stands there. And the controllers that we've seen so far in the exercise would first phrase that as an inverse kinematics problem. So you would say, in order to stand there, what are the joint angles that I need? And then for each joint angle, we would set a PD controller, potentially with some gravity compensation. Once you've done this, your robot tries to behave almost like a chair or a table, in the sense that the legs, they're not rigid, but they're controlled to be rigid. And with a biped, that's maybe not a problem, but think about having a quadrupedal robot, and you do this control. So you say, okay, I'm standing on flat ground, that's my assumption. All the legs should be the same. I control them, the joint angles, that all legs have the same length. And then your ground isn't flat, and one of your feet is standing on something that's a little bit higher. It's going to be the same effect as having a table standing on non-even ground, and you will basically get this unstable rocking motion, right? So from a robotics perspective, it's often better to have a robot that somehow behaves soft, right? So you don't want to have high gains PD controllers or even PID controllers, but you want a controller that's PD but with very low gains to have an adaptive behavior, to be soft, right? Of course, if you have low PD gains, your robot is going to be a little bit the lazy bot, right, hanging out there. Because you have gravity and other things. And with PD control, you have steady state error. So we do feed forward, right? So we do gravity compensation. And then you can basically be soft, but you still have no steady state error, right? So this is why in our exercise, we ended up doing PD control plus feed forward, right? So we get good tracking, but we are also soft in a sense. If something unexpected happens, we have a little bit of give or softness in the robot. And you can imagine if a robot that is controlled this way, the soft way, if I put that on uneven terrain, then that one leg is going to be a little bit elastic. Huh? Maybe not what we care about. Right? Because if you think about a robot, you typically don't care about what the individual joint angles are doing. What you care about is what is the end effector doing, right? This is why when we look at plots in our exercises, we didn't look at joint angle plots, but we're looking at what is the motion of the end effector. Is it moving in a straight line, right? That was our goal. So the controller and our goal are working in different spaces. And it may be better to start thinking about controlling the robot directly in the space in which we're interested in. And this idea of virtual model control is something that goes in this direction and that also nicely uses constraint forces and projections to achieve that. And for a legged robot, my task space, as I will call it, right, isn't the end effector space, but I would say the torso. Right? If I think about a robot should be standing there, I don't care if it's doing this or doing that, as long as the torso is stably supported above the center of gravity, as long as the torso is upright at a certain height, right? And if I can control that, then my robot can do something, right? Gesture while teaching, right? So I basically care about the torso. And this idea behind virtual model control is that I start by defining my behavior not on joint level, but define my behavior directly for the main body. Meaning, my robot is currently in this position, but should be in this position. Right? I want the robot to be upright at a certain height, right above the center of the support polygon, right about the feet. So I want it in this orientation, and I want its center of mass to be in a particular position. I could now go ahead and create a PD controller on that main body level. But a PD controller on a mechanical system is nothing else than applying virtual spring damper elements. So I can think of this as applying virtual spring damper elements that generate a force that pulls the robot from its current position to its desired position. And there would be also a virtual rotational spring here that would try to orient the main body's orientation. So we generate this desired behavior by having a desired outcome and virtual springs, or virtual, I should say, spring damper elements that pull the robot from its desired position to where it should be. And of course, these cannot be physical, because I can always attach something to the robot at its current position, but I cannot, of course, attach a spring to the world reference frame at the desired position. That would never work. But I can now compute what these forces, or what these springs would create in terms of forces and torques. So we, as a second step, we can go ahead and compute the resulting virtual forces, and I'm going to call them F. And these are three-dimensional, right? Because it's, depending on planar robot, two-dimensional, otherwise three-dimensional forces. And of course, we have torques or moments that we will call M. And they should be applied, right? So there's a force F that corresponds to the force generated by this spring, and there is a torque M that is generated by this torsional spring. And up to now, this is not much different than traditional PD control on joint level. I could make an analogy between a PD controller on joint level and a spring damper on that joint. I say, here's the joint. It should be in this position. I attach a rotational spring and a rotational damper. And that rotational spring and rotational damper, which is basically just velocity times damping constant plus displacement times stiffness, gives me a force and a torque, or in this case, of course, just a generalized torque. And I would be here at step 2, and then step 3 is send that virtual spring force to your motors as a motor command. Right? So tau equals, and this is a PD controller, tau equals k times q minus q desired plus d times q dot minus q dot desired. That's your PD controller. So up to this point, I've done the same thing. I apply a PD controller to the position of the main body. Then I can say, well, if I just do PD control, I will have some steady state error. So I should maybe go ahead and do a little bit of gravity compensation. So if I know that this main body has some mass that pushes me down, I should compensate for that by applying a virtual gravity compensation. So this would be step 3. Also something that we did on our joint level controllers. Compute gravity compensation. Right, and we called this minus G. And as a side note, this is not in the original paper, but you can think about adding other things as well, right? I could add, for example, compensation for the Coriolis and centrifugal forces as well, just as we did it in our last exercise. Now, of course, these are virtual forces that live in the Cartesian space, and in that Cartesian space, I don't have a motor. So now things differ a little bit, right? Before, my PD control equations were already living in the generalized coordinates. I had Q minus Q desired, Q dot minus Q desired, and I got an output, a torque tau, that I could send directly to a motor. Here, I have these virtual forces that live in the Cartesian world. And I somehow have to know what are the corresponding motor torques. How do I do this? At this point, you all should know how to do this, because we have projected Cartesian forces, inertial forces, contact forces. We just need to use the appropriate Jacobian. Right? Just as a contact force has a contact Jacobian, just as an inertial force had the Jacobian of the center of mass, here we can do a projection. And this is one of the main reasons why I wanted to show you this, because these projection methods, right, they allow you to create simulations of rigid body systems. But what I really want you to be is creative, right? How can I use these methods to solve other problems? And here's a creative way of saying this. I can use the same method to project these virtual forces into our generalized coordinate space. So what we will do is we will project F, M, and the gravity compensation into the generalized coordinates. And the resulting torque, I will call this tau desired, right? These are my desired generalized torques. And since these forces, at least the way I drew this, have been applied at the center of gravity, I can just use our Js and our Jr of the main body. So Js transpose times F plus Jr rotational Jacobi of the main body transposed times M. Right? So we got to learn this equation as an equation that describes dynamics, but it can also be used here in the sense of a controller. What do I do with G? This gravity compensation vector. How do I project this? Well, I don't, because it is something that already lives in the generalized coordinates. So I can just say minus G, right? Because these are the generalized gravitational torques. Behind the scenes, right, G, of course, is J transpose times F active or Fg in Cartesian coordinates. So you also have Jacobis behind that. And then I could also, if I want to, compensate for Coriolis and centrifugal forces. And now, am I done? One could think so, right? You say I have this tau desired, and now I will send this tau desired to my motors. And it will have the same effect as applying these virtual springs. But there's going to be a problem. The problem is that this tau desired for this particular example, where's my robot, lives in my q space, right? And my generalized coordinates, my vector q in this case, was given by x, y, phi, and then I had my joint angles, alpha L, alpha R, leg length on the left side, leg length on the right side. And correspondingly, of course, my vector of generalized coordinates is going to be an fx, an fy, a tau phi, tau alpha L, tau alpha R, and FLL, FLR. Details don't matter. Those three here are important. Because if I look at these generalized torques and compare them with my actual robot, I don't have motors on all 7 of them. I have motors at the hip joints that can produce here a tau LR and the tau alpha R, tau alpha L, and I have motors at the leg extension, right? Within the legs, I do have motors. Here it's called tau, here it's called F, same thing, right? Tomato, tomato, it doesn't matter. But of course, I don't have torques and forces here because the first 3 coordinates, that's a virtual 3 degree of freedom joint, right? That's just there to describe the position of my main body, and the forces here should be 0 because there's no motor attached. If I apply a force here, it basically means someone from the outside grabs the robot by its center of mass and pulls it up, pushes it to the right, creates an orientation. These would be external torques, right? And if I have them available, this whole problem of controlling a legged robot would be simple because it's just grab it and hold it, right? And that's, of course, not what we want. So we have a bit of a constraint here that, how did I call this on the previous page? Fx equals Fy equals tau phi equals 0. Because we have this virtual 3 degree of freedom joint. So I cannot generate tau desired, right? If this tau desired has values on the first 3 elements, I cannot generate it. That's weird, right? Because the math is basically the same for me. I can say I want to be here, so I virtually apply a force, and I somehow, apply a spring, and that gives me a force on my hip, and I somehow can very well replicate the effect of a spring force on my hip. So somehow I'm physically able to generate these forces, even though there's no one behind me grabbing me, moving me up and down. So there has to be some way how I create these forces. Where do they come from? Right? What keeps me upright? Because if I wouldn't be able to do this, right, I also wouldn't be able to do gravity compensation, and I would just fall through the floor. So where do these forces come from? Here are my equations of motion, right? M, battery is low. Oh, shoot. This is doomed. M times Q double dot plus F plus G. Those are our equations of motion. And then I will write this here as a selection matrix times the motor torques, tau M. What I mean with the selection matrix is it's a matrix where my first 3 rows are just a bunch of zeros, and the last 4 rows are an identity matrix. And you can kind of see that if I multiply this with tau motor, where tau motor, would be my tau alpha left, tau alpha right, and so on. You would basically see that the product here gives me zeros on the first 3 rows and then the motor torques on the bottom 4 rows. So that somehow encodes this constraint that my motors, that the virtual 3 degree of freedom joint doesn't have any motors. There's something missing here. What is missing? Contact, right? We're talking about a legged robot that has 2 feet on the ground. So what I can do here is go ahead and multiply this with our contact forces, which of course get projected into our generalized coordinate space with this matrix J lambda. So J lambda times lambda is the projection of my contact forces. And this is what keeps me up, right? The reason why I don't fall through the ground is because my feet stand on the ground, and that keeps me upright. And now the trick is to say that this here is going to be equal to our desired torques tau. So I'm saying that my desired torques, and this is now basically step 5, I say my desired generalized torques is not only what the motors are doing, but also what the ground is doing. So selection matrix times tau motor plus Jacobi transpose times contact forces. And if we are on the ground, we should be able to solve this, right? Because what is the dimension of this lambda here? What's the dimension of lambda? You say? There's no wrong answer. What did you say? Okay, that's wrong. Pick another number. What's the dimension of lambda? 4 if you have both feet on the ground. X and Y for 2 feet gives you a 4-dimensional constraint space. I was hoping you said 2. I thought I heard you say 2 before. 2, if I have 1 foot on the ground, right, then lambda is 2-dimensional. Contact X and Y on 1 foot. You could also say 0 if both feet are on the ground, then I'm freely in the air. Now you see, right, so here I have 0, 2, or 4 values. Here I have 4, and here I have 7. So I have to create 7 values with either 4, 6, or 8 unknowns. And you can kind of see that this becomes problematic if I have both feet in the air. Then there's 7, here's 4. I will not be able to fulfill this. And this is me falling out of the window, right? I wish that my main body would stay up here and not rapidly move towards the ground, but it's not going to happen, right? There's no control. I'm free falling. Yes?
One question, but like when are on the ground, they are 0, or in that case they doesn't exist?
Same thing, right? This has dimension 0, so the Jacobian is an empty matrix. This doesn't exist. Yeah. Mathematically, it doesn't make a difference. Right? So that's free flight. There's nothing you can do, right? You will follow your ballistic trajectory no matter what. 2, so 1 foot on the ground. Things look a little bit better. But essentially what you generate is 1 foot on the ground and then some robot on top of it. You generated an inverted pendulum. And no matter what you do, this degree of freedom is doomed, right? That's unstable, you're going to fall. And this is what we see here, because then I have 4 here, 2 here, gives me 6 total, still 1 missing, right? So there is 1 degree of freedom that I cannot control. So in a sense, I cannot keep the system upright. If I have 4 here, 2 legs on the ground, then I have 8 unknowns to generate 7 torques, and I should be able to do it, right? These 4 ground contact forces plus my 4 motor torques are able to keep me upright. I can also have a degree of freedom, right? Because I have this extra one, right? There's 8 on the right, 7 on the left. Where's that extra degree of freedom?
You can move up and down.
But that basically means using my torque desire, because that means I generate an upward force, right? And I also can move this way, and then can move that way, and this way, right? So I can generate all the taus that I want. But even without generating a tau, I have some degree of freedom. And you're not going to see it, because if I activate that degree of freedom, nothing is going to happen. I'm activating it right now. You have an idea what I'm doing?
You can stretch out your feet.
I'm pulling my feet together, or I can push them apart. Looks exactly the same to you, because it's sort of a null space of this tau desired. But I can, in a sense, right, if I think about these forces, left foot, right foot, they have a vertical component and a horizontal component. And rather than doing this on one foot and nothing here, I could do this on one foot and that here. And since forces can be moved along their line of action, the effect is going to be exactly the same, right? So that gives me sort of this extra degree of freedom. So this is our step 5, right? Use the contact forces to generate our desired generalized torques, and I'm going to call this tau desired. Here written in a matrix form, right, to sort of see better the number of unknowns and the number of equations, in a sense, that we want to solve. And now we can solve this, and I can do this, for example, in 2 steps. Sorry, how do I get my pen back? Here. This would be the last step. So solve. For example, by separating into, and I will call these now passive with a P, and active with an A coordinates. Passive, of course, the 3 generalized coordinates of the virtual 3 degree of freedom joint. Active coordinates, those that have a motor. So on this side, I would have my passive tau desired. Those would be the first 3. And I would have here my active, sorry, the other way around, tau desired active, the 4 motor torques. And they are equal to, well, these are the first 3 rows of my Jacobian transposed times my lambda desired. And because these are passive, there's no motor torques. So I will say here plus 0. There's no motor torques. And then this would be the bottom 4 rows of the transposed of my Jacobian. And here I do have motor torques, because this is the part where sort of my selection matrix has the identity. So I get here plus the motor torques. And to solve this, now I could first look at the first row, right, which now has this idea of over and under actuation because I have 3 here. I have 0, 2, or 4 here. So for the case of 4 feet in contact, I can solve this. For 2 feet or 0 feet on the ground, I cannot solve this. And once I have computed this lambda desired, I insert it down here and then solve the second equation for our motor torques. And this is a valid controller setup. And did I show you this video at the very beginning of the class? I think so. And I actually want to scroll a little bit. Oh, God. Not allowed to scroll? And there's no sound. My computer is falling apart. You know where there's normally this bar here? Okay, let's do this differently. Let's show you this. So it's one of my undergraduate students who implemented this controller for the robot that we have in the lab. And sort of the nice thing is it doesn't really matter where your feet are on the ground, right? We haven't even reasoned about where's the foot on the ground. Is it even on the ground? Is it in the air? Because, of course, that information somehow goes into these Jacobians. If I lift the foot up, the Jacobians will change, the lever arms will change, the motor torques will change. But in this case, it doesn't matter where the foot is on the ground, because no matter where it is, we're still reasoning about generating these contact forces lambda and then somehow projecting the contact forces through the Jacobians into the generalized motor space. And what Kevin, that's the name of the student, did here on top was to basically add a walking controller where when you have 2 feet on the ground, you fully use this virtual model control concept to stabilize your main body. If there's 1 foot in the ground, you cannot do that anymore, as I showed you. So he only controls orientation and height and passively falls forward. And while he's falling forward, I'm just trying to show you. I think this is the most interesting bit, right? While he's falling forward, he is moving the second leg forward again, right? Replacing that, put it on the ground, and as soon as it's on the ground, he goes back to this virtual model control as I just showed you. In the second video, and this is the one that I thought I showed to you at the very beginning of class, in first lecture, I did. Yeah, I did, right? It's this part here, right, where we say we want an elastic behavior of this robot. I don't know if you remember this, right? Shouldn't bounce around, but should be controlled, actively controlled. What does that mean? You somehow have to compute forces, detect contact, compute forces to the main body, right, our virtual forces that act on the main body. And these virtual forces, in this case mostly damping forces, they are distributed from the main body onto the individual joint. And that's our Jacobi transpose mapping, right? This is exactly this projection that we talked about, right? Take these forces, distribute them into the generalized coordinates. That's J lambda transpose times whatever force we had. And here you see, again, sort of the soft behavior, right? You can push the robot down and it softly reacts. You can lift one of the feet up. It still remains stable because it's not caring where is the foot positioned, but what are the forces applied to that foot. And then, of course, more control to generate the motion. Any questions? Right? Not something that, again, you need to understand in every detail, but I want to show you how powerful these methods are and that they can be used in a different context. And this is what the class should enable you. Right? If you get out of this class and say, yay, I can write a multi-body dynamics engine, congratulations. 50 other people have done this before. Right? And they sell it, so you could have just skipped all of that and buy one. The point is you should understand what's going on to creatively use these techniques to solve other problems. And I think this is a nice example where Jerry Pratt, who's behind this, used these Jacobi transpose mapping to develop a controller. Questions? I have 5 minutes left, and I think it makes sense to use this time to reason or at least to introduce our last topic. Because so far, we have only talked about how to derive the equations of motion. But this class is called computational dynamics, right? Which up to this point was mostly a topic of the exercises. Right? We learned about the equations, and then in the exercises, we implemented it to get a computational tool. Now I want to talk a bit more about algorithms, and I want to talk about how different algorithms behave. And that means, in a formal sense, I want to talk about computational complexity. And computational complexity is something that we typically express in this big O notation, where we think about how does complexity scale with problem size. Problem size typically given by a value n. For a multi-body dynamic system, this could be the numbers of bodies that you look at, or the number of joints. That would be your problem size, NB or NQ. In a general sense, we say n. And that computational complexity can linearly scale with problem size. Twice as many bodies, computation takes twice as long. It could scale quadratically, which would mean twice as many bodies. Computation time goes up by a factor of 4. It can scale to the third power, twice as many bodies, 8 times as long, or 8 times as many computations, or computation time gets 8 times as long. And this is the notation that we're going to use. We call this the big O notation, where we have a big O and then some function of n. And what that means is that the computational complexity is of order whatever fn is. Squared, linear, cubic, and so on. The formal definition is that if I have some function g of n, and this is now exact. Let's say this is the number of floating point operations that your algorithm has. The exact number, which is very hard to get. This is element of order fn. So scales with fn if there exists a positive n naught, so a n naught that is larger than 0, and a constant, let's call it c, also positive, such that for all problem sizes that are larger than n naught, so for what I will then in the future call large n, here is the formal definition, larger than this n naught. This true function, gn, is bounded by c times our order function. right? And this is either smaller or smaller equal. So that's my formal definition. So this Fn somehow gives me an upper bound. It gives me an upper bound for large values, where at some point we have to talk about what large really means. But in this case, larger than n naught. And it gives us an upper bound on scaling, not in absolute terms, because I have this constant c. Right? This could be a million, could be anything, but it exists. Right? So for large n, this can potentially help. And then, of course, what we will do is we will compare different algorithms. And one is going to be order n square, and the other is going to be order n cube. And that order n cube scales worse. Right? Every time I double problem size, it gets 8 times as slow. Whereas the 1n square, every time I double problem size, gets 4 times as slow. So the n square for large n is at some point going to be better. But since we don't know what the c is and what the n naught is, you cannot say it's always better. Right? It's just for large n, at some point it's going to be better. For small n, it could be worse because this constant c for one algorithm is much larger than for the other. So maybe to wrap this idea up, I have one example where I say if my exact number of operations is, what's my example? 5n to the 3 plus, what do I have? 2n to the 2. What is the computational complexity of an algorithm that uses that many operations? N cubed, right? So this is element order n cube. And you can easily show that for this algorithm, c equals 6 and n naught equals 2. So 6 times n to the 3 is basically, yeah. 3, yeah. Sorry. 6 times n to the 3 is this. And from that, I subtract the actual expression, so the magnitude or the absolute value of gn, which is 5n to the 3 plus 2n to the 2. And if that's true, right, this expression should be larger than 0. Everything here is positive, so I can get rid of the absolute values, and this stays the same. And then I get 6n to the 3 minus 5n to the 3 plus 2n to the 2. So that is n to the 3 plus 2n to the 2 is n times, sorry, what do I have? N times yes, minus, because I have my minus sign here. You can see I'm not used to teaching on the board. And then I get 2n squared out of here, and I'm left with n minus 2. And then you can see, right, n squared is always positive. N minus 2 is positive for n larger than 2. So that's where this constant c and this value n naught comes from. So this is the sort of the mathematical formal explanation. We will look at this again in a week from now, and we will look at it more as an algorithm when I say if something scales linearly, I have one for loop that runs from 1 to n. And if I have something that scales quadratically, I have 2 nested for loops. Don't forget about the homework. I'll see you on Thursday for the exercise. Thanks.